Hello chemistry students, welcome to another Module 2 video. In this video we are looking at dot point 2.2.1 and introducing the idea of the mole concept. Now the mole is a new way to measure chemicals and molecules and atoms and all sorts of stuff in chemistry, and it's a highly superior form of measurement compared to any other type of measurement that you've ever seen before in science, when we're looking at the field of chemistry, of course. And I think the best way to sort of start to explain why this form of measurement is so powerful is to show why other forms of measurement may not be as powerful as we think they are. So already we've started to look at balancing equations as we did in the last video. And we saw that we were balancing our equations and looking at how different molecules were interacting with each other by counting the number of molecules that were actually reacting with each other. So in this instance, we said that we had to have 2 hydrogens and 1 oxygen molecule, H2s and O2s, to form 2 lots of water, H2O, and that they all existed in ratios dictated by the number of their atoms rather than the mass of the substance. And so while it may be intuitive to say, hey, if I had 2 grams of hydrogen and 1 gram of oxygen, well, then I'd make 2 grams of water and we'd be hunky-dory. That doesn't exactly make a lot of sense. One, because conservation of mass dictates that here on this side I have 3 grams of substance only to make 2, and that 1 gram hasn't been taken into account. On top of the fact that hydrogen and oxygen don't have the same atomic mass to begin with. So if they don't have the same atomic mass, we can't have our ratio of masses of hydrogen and oxygen follow the ratios of number of particles when we react the reactants and products together and have our ratios of particles here at the top when we balance an equation. The two measurements just don't link up at all. And so when we're working in the lab and we're measuring out substances and we're measuring in grams, we can't just put things in simple ratios in the same way that we've done when we've balanced an equation. We have to be looking at the number of particles, and this can become a little bit problematic. Essentially, we need a better method for measuring chemical reactions, and the method must focus on having a count of particles rather than trying to get a mass or a volume or something like that, because the masses and the volumes do not follow that same ratio of particle count like we've already seen when we've been balancing our equations. Now, the way that I'm going to come to that conclusion is sort of ask a question first and answer it that way. I want you to think about and have a guess before I flip to the next slide. I want you to guess how many molecules of water are in 18 mils of water. So in here, a container of about 18 mils of water, roughly how many particles would there be altogether? Now, the answer is quite large. It is 602 sextillion particles or thereabouts, give or take. An absolutely massive and incomprehensible number. If we were to put this in scientific notation, it would be 6.02 times 10 to the 23, or 6.022 if you were to include this final number there. Sometimes we do for an additional amount of accuracy. And it's known as Avogadros number. You'll find this number here. It's called the Avogadros constant or Avogadros number here, and it's actually got 6.022 on your data sheet. And this is a number that we'll use fairly often in a bunch of different calculations. Now, Amedeo Avogadro is the scientist who is the namesake for the Avogadro constant. Now, he didn't actually come up with this number or anything like that. It was named after him for his work in chemistry, in quantitative chemistry fields, in fact. He was the one that came up with this Avogadros Law. I mean, the law was named after him because he discovered it, but the idea here is that equal volumes of gases under the same conditions of temperature and pressure will contain equal numbers of molecules. And we actually saw this in practice the other day when I showed you this reaction here between with water in it breaking down in what we call a Hoffman voltameter, the piece of glassware that we were using, and we saw that there was roughly double the volume of hydrogen gas produced compared to the oxygen, and we concluded that was because if we balanced out our equation, that there was double the amount of hydrogen produced compared to oxygen if we were to break down water. Anyway, very important scientist, and he was the namesake for the Avogadro constant, even though he didn't have any direct involvement in the development of the number itself. So that leads us to what is a mole, and the mole is really the Avogadro constant, or the mole is related to the Avogadro constant. We have 1 mole of a substance, then we have 6.022 times 10 to the 23 particles of the substance. It's a count of particles itself. And I'm hoping that we can appreciate that doing any kind of mathematics or talking in a way where we're talking about an incomprehensible number like 6.022 times 10 to the 23, that would be quite difficult. It's a lot easier for us to see and understand numbers of particles if we're talking about it with a number that's significantly smaller. So we just say that 1 mole is this Avogadro constant here. And this Avogadro constant has come up in later years being defined against like the number of carbon particles, and I'll look at that a little bit later in this video. Now, these words define quantities. So say a mole, it defines a quantity, but it doesn't actually give the value of the number. There are other numbers that you have experienced or used in day-to-day life that do the same thing. So for example, instead of saying a mole, I could say a dozen eggs. Now, if I had a dozen eggs, that would be 12 eggs. If I had a mole of eggs, I'd have this many eggs, a countless number of eggs. If I was talking about a decade represents 10 years. A mole of years would be 6.022 times 10 to the 23 years. A pair of socks represents 2 socks. A century in cricket is 100 runs in the game of cricket. And if I was talking about 1 grand, usually we'd be talking about money, but a grand generally refers to a count of 1,000. So all of these words represent a count of numbers as well, without actually saying what that number is. The mole acts in exactly the same way. And so mathematically, we can treat them in a very similar way. So as an example, if I have 2 grand, and that's essentially 1 grand times 2, which is $2,000, I can treat my number of moles in a very similar way. If I have 2 moles of a substance, or 2 moles of particles, then that would represent 2 times Na here, which is the Avogadro constant. If you can see here, that's the way that we usually notate it. So in other words, 2 times 6.022 times 10 to the 23 particles. Now, if you multiply that number by 2, you get 1.2044 times 10 to the 24 particles. If I have half a dozen eggs, I take my 12 or dozen eggs and divide that by 2. I end up with 6 eggs at the end. Now, if I have half a mole or 0.5 of a mole, I take the Avogadro constant and divide it by 2. So 6.022 times 10 to the 23, all divided by 2. And that gives me 3.011 times 10 to the 23 particles. Now, I could also have 5 pairs of socks. So 5 times our 2 socks, or our pairs of socks, making 10. Same thing here. If I had 5 moles of a substance, I'd have 5 times the Avogadro constant of particles, or 5 times 6.022 times 10 to the 23 particles. So that would be 3.011 times 10 to the 24 particles. Now that brings us to what a mole looks like in practice. And for every single substance, it's a little bit different. What we'll see is that if I have a mole of zinc, 6.022 times 10 to the 23 particles, they would weigh in total 65.4 grams. And that's actually based on the atomic mass that we were looking at in the periodic table only a few weeks prior. And you'll see that pattern continue on for all of these substances, that the mass of a mole of substance is the same as its atomic weight that we see in the periodic table. So if I have a mole of magnesium, it weighs 24.3 grams. If I have a mole of copper, so again, 6.022 times 10 to the 23 particles of copper, in total, it weighs 63.5 grams. And the pattern goes on for all of them. And what you'll notice is that for every different kind of element, what we will have is a different mass, assuming that we have exactly a mole of that substance. And the masses are completely different for a mole of every single substance because the particles themselves weigh differently. Now, a more modern definition of a mole is the count of particles when we have exactly when we have exactly 12.011 grams of carbon in a sample. That's a more modern definition of the Avogadro constant, but it still equals out to our 6.022 times 10 to the 23 particles. Now, when we move into the next video, what we're going to be looking at are some simple mole calculations, some ways to manipulate these numbers and calculate values for substances in a simple setting. From there, we'll move on and do some more complicated ones in future videos after that. But until next time, have a good one.